Hello, thank you for the introduction. I'm Jaana Haavisto. I'm from the Faculty of Environmental and Biological Sciences. I work at the moment in the research group of Ecosystem and Environment in the University of Helsinki, and I will be a soon-to-be PhD student. So I'm presenting my current research on the relationship between value of information and control in oil spill risk management. And the first title, I think, was trying to maybe get this idea to be more understandable in a common sense, but this is the more harder title then. And the agenda for today is I'll be going through the introduction part, then methods and analysis results and future possibilities. So for introduction, I will maybe give a little bit of insight on the initial ideas that we have between the relationship between research and policies. So if we think about research, it allows us to choose the most beneficial actions in terms of policy implementation. Because as we know, without information, it is very hard to form advised policies or options. We have more uncertainty about the efficiency, the outcome, and also possibly more economic losses. And then with policies, they help us, of course, to reach the most desired state of the system, the outcome that we want. We need policies for to get to that outcome. And of course, only knowledge does not result as changes. We need the actions to reach these outcomes that we want. So then without policy implementation, possibly we can't affect the system. So this is kind of the relationship between knowledge and policy implementation, information controllability. And this is, of course, the question for the policymaker as well. For example, in ministries, they need to decide on allocating resources between policy implementation and further research. And how to do that, that can be very hard to tell. How should the allocation be then? There are, however, only a few published papers looking at this relationship between controllability and information. One example is the paper by Fenwick and others who modeled the implementation of new healthcare technology and tried to include what we have in real life, that policy implementation is not perfect. We can't have perfect policy implementation. Usually that's not the real life, but in modeling analysis, that is what we assume, that the policy implementation is perfect and immediate as well. So then my research questions were to explore the relationship between value of information and value of control, and in my case I tried to do that in Bayesian influence diagrams, and then to have kind of ideas how to advise with these results the implementation or the allocation of resources between policy implementation and information. So, like I said, I used Bayesian networks or so-called influence diagrams to analyze this. Bayesian networks, they are causal probabilistic networks. They consist of these random variables called uncertainty nodes and then arcs between them that tell about the hierarchies or dependencies between the variables. And the variables contain information in kind of probability distributions in a form that can be consisted of current data or expert knowledge or simulations. And then influence diagrams are similar to this, but they also have additional nodes for decisions and then utilities. So influence diagram as a name is quite good, as it tells us how this decision will influence our utilities in this network. And then I used this published space and decision model by Helle et al. To my analysis. It is a cost-benefit analysis model that consists of two management policies, one of them being automatic alarm system that is a preventive pre-spill policy, and then the other one is new oil company vessel, which is a post-spill policy measure. Here is the model. In both of the corners or upper corners we can see the decisions. The green ones are the costs, and then there are also this external damage function, which describes the environmental benefits of not having oil in the Baltic Sea. And then the blue one in the left upper corner is what I introduced in this model. It's an uncertainty node for the implementation of this alarm system. According to this network, the alarm system is the most, or is the cost beneficial policy implementation that should be chosen. So that's why I wanted to include this uncertainty to this policy decision to see how sensitive it might be to the introduction of different policy implementation uncertainty levels. And then value of information, of course, it tells us how much we gain if we know or we could observe the true state of variable before making the decision. So then value of information basically is it is calculated with the expected maximum value, which is the knowledge with the uncertainty, and then with perfect information. So it is the difference between information under perfect certainty and uncertainty. And then value of control in this is modeled with uncertainty. Or, of course, if we would, well, let's say that we have the uncertainty in the outcome of policy. So in this case, in this model, it is the annual number of collisions after we implement the alarm system that we are looking at in this case. And from the previous research, which has explored the possibility of perfect controllability and how that affects the value of information, if we have better control over the outcome that we want, then value of information decreases because we don't need any more of information because we already have the higher probability to reach the outcome that we want. So I wanted to explore what happens to the value of information when in real life we don't have the controllability that we assumed to have based on previous knowledge. So to do so, I introduced the uncertainty between the decision and the outcome, and I used two approaches for creating this uncertainty because in the probability distribution, the uncertainty is, well, it is based on these two approaches, how to allocate the probability to the distribution more evenly so that it is more uncertain. So the first approach is then the proportional covariation method, and it deducts the probability mass from the most probable option, which is in this case is 0 accidents, and then allocates it between the other scenarios, which are 1 to 6 accidents per year, based on their proportional sizes. So with this method or approach, then it distributes the probability mass mostly to 1 accident per year, because proportionally it is the more probable outcome to happen. Which of course, it's what I wanted to do is look at the effects of no control in value of information. So this does not approach this no uncontrollability, because we still have some information in the probability distribution. And then the second approach to reach the uniform or uncontrollability in the probability distribution, I use the uniform covariation method that is order preserving, so that maybe we could better see how this no control or information, how that affects the need for further information. So then for results, or maybe I explain first. So the results are then conducted for each level of uncertainty, which are between numbers 0 to 10, 0 being no added uncertainty, and 10 being then the maximum uncertainty. And for both approaches, the proportional and the uniform. And then with only the alarm system, without the possibility to having the other policy option, which is the vessel, in the analysis as well. So first only for the alarm system, and then having both of the decisions in the analysis as well. So this is value of information results for the first approach, which was the proportional covariation method, and then without the possibility to observe new vessel in the analysis. So we can see that we don't have value of information with only the alarm system, and for this method only for the highest level of uncertainty, which is mostly that we have 1 accident per year, and that we can't really control it. So this does not then maybe represent the no control in the distribution, like I assumed as well. So the value of information increases for the higher levels of uncertainty. And then for the uniform distribution or covariation method without the new vessel, we can see that now value of information starts to increase in level 2 and increases all the way up to level 9, and then decreases to 0 when we have the uniform distribution. So if we don't have the control, we don't really need the information in this according to this result. And then this is for the, again, proportional covariation, but now we have both policies in the analysis. So now we can see the optimal policy decisions in the blue area. In this case, the alarm system is always optimal, and the new vessel has been unoptimal from the beginning. But now we can see that first, if you look at the value of information, it increases to the point of level 3, and then decreases after that when we go to level 4. And this is the point where we also implement the new vessel. So the need for, or how the information in this point after this certain threshold, it cannot anymore support this decision to only implement the alarm system. We also need the other policy option as well. So then our need for further information decreases. Of course, now there is value of information from the new vessel as well, because it is included in the analysis, which we can also see that now that we, in this uniform covariation method, in this case it doesn't decrease to 0 because we have the new vessel in the analysis as well. But now we can see that the kind of shape is similar than we had in the previous results, which is that after certain point, value of information first it increases and then starts to decrease, and the optimal decision is to implement the vessel as well. I am running out of time, but so to conclude these results is that, of course, these are methods to maybe include the possibility of implementation uncertainty that is in real life. Our policies might not present like we hoped for. So what does that then do to our the optimality of other decisions or the need for further information, and in what variables? So testing this models with the implementation uncertainty can be beneficial then. And for future possibilities, of course, now that with the Russia's actions in Ukraine, we can see that we have more uncertainty in the Baltic Sea regarding new unknown vessels going around, and maybe, or I would say we have more uncertainty, of course, in the effectiveness of our current oil spill risk management policies as well. We don't know anything about these tankers, and that, in my opinion, increases our risks of maritime oil accidents. So then, of course, that should be explored in the modeling as well. And then what has been discussed earlier yesterday was the improvement of scientific cost effectiveness through cooperation in the Baltic Sea, and the possibility of including these benefits and costs in modeling as well, I think should be discussed more. And for me, the testing of these methods will be also in different types of influence diagrams, and then, of course, more analysis about the effects on different variables that we need more information about, and the sensitivity of these variables to the uncertainty. And then, of course, the possibility to include, or how could we include the relationship of businesses in this case? As also mentioned yesterday, businesses can be a beneficial provider in the research funding. So how these benefits of research to the businesses, could that be modeled as well better in our analysis? And okay, that is from me this time. Thank you very much for listening. And
thank you very much.
Thank you.
Time for questions. Pentti.
Well, first of all, thank you for the presentation. Thank you for using our Bayesian model, because I was also involved in to make the model 2015 and Helle published. So it's very nice that somebody will continue the work. So I have maybe some difficult question for you. If the uncertainty is so important parameter, how we can affect on to make uncertainty small?
to make uncertainty smaller.
And how we can affect to uncertainty, because it seems to be very important parameter in the. It's very important. So how we can affect the most important parameter, uncertainty? It's a difficult question, I know, but let's see.
That is the good question. Thank you for that. Well, research, of course, with knowledge, we can decrease the uncertainty, but then, of course, we need the actions there as well. How can we only decrease the uncertainties with knowledge if we don't know how to, or do not implement this information into action and do it effectively as well?
And very good luck for your doctoral. I wait for the
Thank you.
doctoral results. It's very important topic what you're doing.
Thank you.
More questions? Actually, I have one question which was related to this Russian oil spill. Possible oil spill. So could you tell something more about these risks? I don't quite understand if you think that the risk is increasing and why, if it's so.
Well, the risk for possible oil spills.
Yeah.
Of course, there can be multiple risk increasing factors. In this case, with the process actions and how we have more unknown tankers going on that have they are not so in good condition, possibly, but we don't know. We don't know basically anything about them. So that's the uncertainty, I think. How are then our current pre-spill measures? Are they affecting these unknown tankers as well? So that, in my opinion, increases the risk for oil spill catastrophes in the Baltic Sea.
Okay. I hope that our decision makers also are aware, or the politicians are aware of this situation. Okay, do we have some other questions still? I don't see now any hands. Thank you for this very interesting presentation again.
Thank you.